In mathematics, the absolute value or modulus x of a real number x is the non-negative value of x without regard to its sign. Namely, x equals x for a positive x, x equals minus x for a negative x, and 0 equals 0. For example, the absolute value of 3 is 3, and the absolute value of minus 3 is also 3. The absolute value of a number may be thought of as its distance from 0. Generalizations of the absolute value for real numbers occur in a wide variety of mathematical settings. For example, an absolute value is also defined for the complex numbers, the quaternions, ordered rings, fields and vector spaces. The absolute value is closely related to the notions of magnitude, distance, and norm in various mathematical and physical contexts, terminology and notation. In 1806, Jean-Robert Argand introduced the term module, meaning unit of measure in French, specifically for the complex absolute value, and it was borrowed into English in 1866 as the Latin equivalent modulus. The term absolute value has been used in this sense from at least 1806 in French and 1857 in English. The notation x, with a vertical bar on each side, was introduced by Carl Weierstrass in 1841. Other names for absolute value include numerical value and magnitude. The same notation is used with sets to denote cardinality. The meaning depends on context, definition and properties. Real numbers: for any real number x, the absolute value or modulus of x is denoted by x, and is defined as can be seen from the above definition. The absolute value of x is always either positive or 0, but never negative. From an analytic geometry point of view, the absolute value of a real number is that number's distance from 0 along the real number line. And more generally, the absolute value of the difference of two real numbers is the distance between them. Indeed, the notion of an abstract distance function in mathematics can be seen to be a generalization of the absolute value of the difference. Since the square root notation without sign represents the positive square root, it follows that which is sometimes used as a definition of absolute value of real numbers. The absolute value has the following four fundamental properties. Other important properties of the absolute value include two other useful properties concerning inequalities are. All these relations may be used to solve inequalities involving absolute values. For example, absolute value is used to define the absolute difference, the standard metric on the real numbers. Complex numbers: since the complex numbers are not ordered, the definition given above for the real absolute value cannot be directly generalized for a complex number. However, the geometric interpretation of the absolute value of a real number as its distance from 0 can be generalized. The absolute value of a complex number is defined as its distance in the complex plane from the origin using the Pythagorean theorem. More generally, the absolute value of the difference of two complex numbers is equal to the distance between those two complex numbers, for any complex number where x and y are real numbers. The absolute value or modulus of z is denoted z, and is given by when the imaginary part y is 0. This is the same as the absolute value of the real number x. When a complex number z is expressed in polar form as with r0 and theta real, its absolute value is. The absolute value of a complex number can be written in the complex analog of equation above as, where z is the complex conjugate of z. Notice that, contrary to equation, the complex absolute value shares all the properties of the real absolute value given in equations above. Since the positive reals form a subgroup of the complex numbers under multiplication, we may think of absolute value as an endomorphism of the multiplicative group of the complex numbers. Absolute value function. The real absolute value function is continuous everywhere. It is differentiable everywhere except for ex equals 0. It is monotonically decreasing on the interval. Since a real number and its opposite have the same absolute value, it is an even function, and is hence not invertible. Both the real and complex functions are idempotent. It is a piecewise linear, convex function. Relationship to the sign function. The absolute value function of a real number returns its value irrespective of its sign, whereas the sign function returns a number's sign irrespective of its value. The following equations show the relationship between these two functions. Or and for x0, derivative. The real absolute value function has a derivative for every x0, but is not differentiable at x equals 0. Its derivative for ex0 is given by the step function. The subdifferential of x at x equals 0 is the interval -1, 1. The complex absolute value function is continuous everywhere but complex differentiable nowhere because it violates the Cauchy-Riemann equations. The second derivative of x with respect to x is 0 everywhere except 0, where it does not exist. As a generalized function, the second derivative may be taken as 2 times the Dirac delta function. Antiderivative. The antiderivative of the absolute value function is where c is an arbitrary constant of integration. Distance. The absolute value is closely related to the idea of distance. As noted above, the absolute value of a real or complex number is the distance from that number to the origin, along the real number line, for real numbers, or in the complex plane, for complex numbers, and more generally, the absolute value of the difference of two real or complex numbers is the distance between them. The standard Euclidean distance between 2 points in Euclidean n space is defined as. This can be seen to be a generalization of a minus b, since if a and b are real, then by equation, while if and a complex numbers. Then the above shows that the absolute value distance for the real numbers or the complex numbers agrees with the standard Euclidean distance they inherit as a result of considering them as the 1- and 2-dimensional Euclidean spaces, respectively. The properties of the absolute value of the difference of two real or complex numbers, non-negativity, identity of indiscernibles, symmetry and the triangle inequality given above, can be seen to motivate the more general notion of a distance function as follows. A real-valued function d on a set x times x is called a metric on x, if it satisfies the following 4 axioms. Generalizations. Ordered rings. The definition of absolute value given for real numbers above can be extended to any ordered ring. That is, if A is an element of an ordered ring R, then the absolute value of A, denoted by A, is defined to be where -A is the additive inverse of A, and 0 is the additive identity element. Fields. The fundamental properties of the absolute value for real numbers given in above can be used to generalize the notion of absolute value to an arbitrary field, as follows. A real-valued function v on a field f is called an absolute value if it satisfies the following 4 axioms. Where 0 denotes the additive identity element of f, it follows from positive definiteness and multiplicativeness that v equals 1. Where 1 denotes the multiplicative identity element of f. The real and complex absolute values defined above are examples of absolute values for an arbitrary field. If v is an absolute value on f, then the function d on f times f, defined by d equals v, is a metric and the following are equivalent. D satisfies the ultrametric inequality for all x, y, z in f, is bounded in R, for all. An absolute value which satisfies any of the above conditions is said to be non-Archimedean, otherwise it is said to be Archimedean. Vector spaces. Again, the fundamental properties of the absolute value for real numbers can be used, with a slight modification, to generalize the notion to an arbitrary vector space. A real-valued function on a vector space V over a field F, represented as, is called an absolute value, but more usually a norm, if it satisfies the following axioms. for all R in F, and V, U in V. The norm of a vector is also called its length or magnitude. In the case of Euclidean space Rn, the function defined by is a norm called the Euclidean norm. When the real numbers R are considered as the one-dimensional vector space R1, the absolute value is a norm, and is the p-norm for any p. In fact, the absolute value is the only norm on R1, in the sense that, for every norm on R1, x equals 1, x. The complex absolute value is a special case of the norm in an inner product space. It is identical to the Euclidean norm, if the complex plane is identified with the Euclidean plane R2.